Welcome to our physics lesson on electrostatics. Today we'll explore the fascinating world of electric charges and the phenomena they create. Electrostatics is the study of electric charges at rest and the forces, fields, and potentials they produce. It's the foundation for understanding how stationary electric charges interact with each other and with materials around them. Let's start with the fundamental concept: electric charge. There are two types of electric charges in nature: positive and negative. Like charges repel each other, while opposite charges attract. Charge is quantized, meaning it comes in discrete amounts that are multiples of the elementary charge E, which is approximately 1.602 times 10 to the negative 19 coulombs. And charge is conserved. The total charge in an isolated system remains constant. Charges can move around or redistribute, but the net amount doesn't change. Now, let's discuss how materials respond to electric charges. Materials can be broadly classified into conductors and insulators based on how easily charges can move through them. Conductors, like metals, allow charges to move freely. When excess charge is placed on a conductor, it quickly spreads out over its surface. Insulators, like rubber or glass, restrict charge movement. Any excess charge stays where it's placed on an insulator. Common conductors include metals like copper and aluminum, while common insulators include rubber, plastic, and glass. Coulomb's law is the mathematical foundation of electrostatics. It quantifies the force between two-point charges. The formula states that the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. Mathematically, we express it as F equals 1 over 4 pi epsilon 0 times the absolute value of Q1 times Q2 divided by R squared. Here, F is the force in newtons, Q1 and Q2 are the charges in coulombs, R is the distance between them in meters, and epsilon 0 is the permittivity of free space, approximately 8.85 times 10 to the negative 12 c squared per newton meter squared. The force acts along the line connecting the charges. If the charges have the same sign, the force is repulsive, pushing them apart. If the charges have opposite signs, the force is attractive, pulling them together. Now, let's discuss the electric field concept. An electric field is a region of space where an electric charge experiences a force. It's a way to describe how charges influence their surroundings. Mathematically, the electric field at a point is defined as the force per unit positive test charge placed at that point. For a point charge, the electric field is given by E equals 1 over 4 pi epsilon 0 times Q over R squared times R hat, where R hat is the unit vector pointing from the charge to the point of interest. Physically, this means that if you place a small positive test charge in an electric field, it will experience a force given by F equals Q0 times E. We often visualize electric fields using electric field lines. These lines point away from positive charges and toward negative charges. The density of these lines indicates the strength of the field. More lines means a stronger field. The superposition principle is crucial for understanding complex electric fields. It states that when multiple charges are present, the total electric field at any point is the vector sum of the fields produced by each individual charge. Mathematically, we express this as E total equals E1 plus E2 plus, and so on for all charges present. Let's visualize this. Here we have two charges creating their own electric fields. When we combine them, the resulting field at any point is the vector sum of the individual fields at that point. For continuous charge distributions, like charged lines, surfaces, or volumes, this sum becomes an integral over the entire distribution. Now, let's discuss electric dipoles, which are fundamental in many physical systems. An electric dipole consists of two equal and opposite charges separated by a small distance. The dipole moment is a vector quantity that characterizes the strength and orientation of a dipole. It's defined as P equals Q times D, where Q is the magnitude of either charge, and D is the vector pointing from the negative to the positive charge. Dipoles create distinctive electric field patterns that differ from single charges. Close to the dipole, the field is complex, but far away, it falls off more rapidly than the field of a point charge, as 1 over R cubed rather than 1 over R squared. When placed in a uniform electric field, a dipole experiences a torque that tries to align it with the field. This torque is given by tau equals P cross E. It also has potential energy that depends on its orientation. U equals negative P dot E The energy is lowest when the dipole is aligned with the field. Energy plays a crucial role in electrostatics. Moving charges in an electric field requires work, which is stored as potential energy. For 2-point charges, the potential energy is given by U equals 1 over 4 pi epsilon 0 times Q1 times Q2 divided by R. This represents the work required to bring the charges from an infinite separation to a distance r apart. If the charges have the same sign, the potential energy is positive, meaning work must be done against their repulsion. If they have opposite signs, the potential energy is negative, as the charges naturally attract each other. We can also express energy in terms of the electric field itself. The energy density in an electric field is proportional to the square of the field strength. Electrostatics has numerous real-world applications. Static cling is an everyday example where clothes stick together due to the transfer of electrons creating opposite charges that attract. Lightning is a spectacular, natural demonstration of electrostatics. Charge separation in clouds creates enormous potential differences, eventually resulting in a dramatic discharge. Technologies like photocopiers and laser printers rely on electrostatic principles to selectively attract toner particles to create images. Electrostatic precipitators in industrial settings use electric fields to remove particles from gas streams, helping reduce air pollution. Let's summarize what we've learned about electrostatics. We've covered the fundamental concepts of electric charge, the interactions between charges described by Coulomb's law, and how these interactions create electric fields. We explored how the superposition principle allows us to analyze complex charge arrangements, and we examined the special case of electric dipoles. We also discussed the energy aspects of electrostatic systems and looked at some real-world applications. These principles form the foundation of electromagnetic theory and have widespread applications in physics, engineering, and everyday life. Thank you for watching.